For the first time in the history of Earth science, researchers have watched one of the planet's most powerful geological engines in the literal act of dying. Off the coast of Vancouver Island, just north of the stretch of ocean floor that threatens the Pacific Northwest with a magnitude 8 or 9 megathrust earthquake, scientists using seismic imaging technology have captured a tectonic plate tearing itself apart piece by piece, roughly 5 kilometers of seafloor dropping, suddenly along a fault line that researchers say is close to breaking clean through. This is not speculation built from ancient rock formations or computer models alone. This is a subduction zone, the exact type of boundary responsible for the largest earthquakes and the most explosive volcanic eruptions on the planet, caught directly in the act of shutting down, something geologists have theorized about for decades without ever actually witnessing it happen in real-time until now, a gap between theory and direct observation that has quietly persisted across an entire generation of earth science research. This is the story of what researcher S actually found beneath the seafloor off Vancouver Island, why this discovery finally answers a question that has puzzled geologists for generations, and what the scientists behind this study say it genuinely does and does not mean for earthquake risk across the Pacific Northwest. No exaggeration, just what the journal Science Advances, Louisiana State University, and Columbia University's Lamont Doherty Earth Observatory are actually reporting. Drop a comment and tell me if you live anywhere across the Pacific Northwest, Washington, Oregon, British Columbia, or Northern California, because I want this video to reach the people who actually live above, the broader tectonic system this discovery is part of. I read every one of these. If you want grounded science coverage instead of recycled panic, subscribe. It is free. An A-like helps this reach people before a less careful version of this story does. Let us go for 5,000 likes on this one. Now let us get into it. To understand why this discovery genuinely matters to geologists worldwide, you first need to understand what a subduction zone actually is, and why scientists have spent so long trying to understand how one eventually comes to an end. A subduction zone forms wherever one of Earth's tectonic plates, the massive slabs of solid rock that make up the planet's outer shell, dives beneath a neighboring plate and sinks down into the mantle below. That process is responsible for building mountain ranges, triggering the planet's most powerful earthquakes, fueling explosive volcanic eruptions, and slowly recycling old ocean floor back into the deep earth over millions of years. A cycle that has shaped the surface of this planet since long before anything resembling modern geography existed. Subduction zones can persist for tens of millions of years, but nothing in geology lasts forever, and scientists have long known that these systems eventually stall and shut down, typically when an unusually thick or buoyant section of oceanic crust reaches the boundary and resists sinking the way thinner, denser crust normally would. Oceanic crust formed near a mid-ocean ridge where fresh material continuously wells up from the mantle, tendes to be hotter, thicker, and less dense than older, colder crust farther from that ridge, which means a plate is rarely uniform along its entire length. Some sections sink easily while neighboring sections resist, and it is precisely that resistance that eventually generates the kind of internal stress capable of tearing a plate apart rather than allowing it to subduct smoothly as one continuous sheet. What nobody had ever actually observed directly until this study was what that shutdown process physically looks like while it is happening, whether a dying subduction zone collapses all at once or comes apart more, gradually, piece by piece, a distinction that matters enormously for understanding how the largest earthquakes and volcanic systems on the planet actually behave as they approach the end of their geological life cycle. The answer, according to this new research, is unambiguous. Rather than shutting down cleanly in a single unified collapse, the subduction zone off northern Vancouver Island is tearing apart in stages, breaking into smaller fragments researchers call microplates, with each new piece splitting off before the process repeats itself further along the boundary. Brandon Schuck, an assistant professor at Louisiana State University and the study's lead author, described the process plainly, explaining that rather than shutting down all at once, the plate is ripping apart piece by piece, comparing it at one point to a train slowly derailing rather than crashing in a single dramatic instant. That distinction, gradual fragmentation instead of sudden collapse, is exactly the kind of detail that had remained theoretical for decades, inferred only from studying fossilized remnants of ancient, long-dead subduction zones preserved in rock formations elsewhere on the planet, never confirmed by watching an active system do it in real time. The research team, which also included Brian Boston, Suzanne Carbat of Columbia University's Lamont Doherty Earth Observatory, Shuo Han, Ann Basel, and several additional co-authors, gathered their evidence using a technique Schuck compared to an ultrasound of the Earth, sending sound waves down through the ocean floor and recording how they reflected back to build a detailed image of the rock layers and fault, structures far below the seafloor's surface. That imaging revealed the clearest picture yet of exactly where and how this specific subduction zone is coming apart, centered on the boundary where the Juan de Fuca and Explorer plates, two smaller oceanic plates that have historically both been sliding beneath the much larger North American plate, meet near a genuinely complicated intersection of ridges, trenches, and fault lines just offshore northern Vancouver Island. At the heart of that intersection sits a structure called the Nootka Fault Zone, which the research team found is actively slicing the incoming oceanic plate into distinct separate pieces, allowing some fragments to stall or peel away entirely, while neighboring sections continue subducting normally, all within the same relatively narrow stretch of ocean floor. The specific physical evidence behind this finding is genuinely striking on its own. Along one identified fault, the research team measured the underlying slab of oceanic crust dropping by approximately 5 kilometers, roughly 3 miles, a dramatic vertical displacement that indicates the plate is not simply bending or flexing under stress, but is actually separating along a clean structural break. Carbot has been explicit about why catching this specific moment matters so much scientifically, noting that geologists have understood for decades that subduction can stall when a buoyant section of oceanic plate reaches the trench, but that researchers had never previously had this clear a picture of the actual breakup process happening in real time, rather than reconstructed after the fact from evidence millions of years old. Based on the current trajectory of this tearing process, the research team's longer-term projections suggest the active subduction margin in this specific region will eventually shorten by roughly 47 miles once the Explorer plate segment is fully separated and effectively captured by the neighboring Pacific plate, a shift that would also likely relocate the nearby triple junction where multiple plate boundaries currently intersect, and gradually strengthen the corridor that currently functions as a looser shear zone. A more clearly defined transform boundary, the same basic type of fault system as California's famous San Andreas. This is not the only recent finding reshaping scientists' understanding of the broader Cascadia system either. Separate research examining small, low-frequency earthquakes near this same general triple junction has found the underlying geology considerably more complex than earlier models assumed, describing what amounts to 5 distinct moving pieces of crust interacting in this specific corner of the Pacific, rather than the simpler 3-plate picture long used in textbook descriptions of the region. Taken together with this new tearing study, that growing body of research paints a picture of northern Cascadia as a genuinely intricate, actively evolving junction of multiple smaller tectonic pieces, a considerably more complicated system than the comparatively uniform megathrust boundary running along most of the Oregon and Washington coastline further south, and a reminder that even a region as extensively studied as this one continues to reveal new layers of structural complexity as monitoring technology and imaging techniques keep improving year after year. It is worth being genuinely precise here about what this discovery does and does not tell us about earthquake risk across the Pacific Northwest, because that distinction is exactly the kind of nuance that tends to get lost once a headline starts using words like breaking apart. Carbot and her co-authors have been direct on this specific point, stating clearly that this research does not change the known hazard from the region's main megathrust system, the roughly 700-mile-long stretch of the Cascadia Subduction Zone running from Northern California up through British Columbia, where the Juan de Fuca plate continues sliding beneath North America at a rate of about 4 centimeters a year and remains capable of producing a devastating magnitude 8 or 9 earthquake. The tearing this new study documents is occurring specifically at the northern, structurally more complicated edge of that broader system, near Vancouver Island, where multiple smaller plates and fault zones already interact in ways considerably more intricate than the more uniform megathrust boundary running along the bulk of the Oregon and Washington coastline. Lamont Doherty's own summary of the research was explicit enough to title its coverage around the idea that this discovery is not necessarily bad news, framing it instead as a genuinely valuable scientific window into how these systems evolve and eventually shut down, information that sharpens hazard models rather than raising the underlying threat level facing the region's largest population centers. That said, the discovery does carry real meaningful implications for how scientists model earthquake risk going forward, just not in the way a more sensational framing might suggest. Understanding precisely how a slab tears, rather than assuming it simply behaves as one uniform, continuous plate helps researchers build more accurate models of where stress concentrates along the boundary and how a future rupture might actually propagate through a segmented, fractured system rather than tearing through as a single uniform sheet of rock. Seeing this tear happening now, rather than only inferring it from ancient geology, allows scientists to test those updated models against real, observable data for the first time, a genuinely significant methodological upgrade, even though it does not, on its own, indicate the broader Cascadia hazard has grown more severe or more imminent than what seismologists already understood before this study was published. Schuck and his colleagues have framed this contribution specifically in terms of settling a decades-old open question in their field, how these massive systems actually end, rather than in terms of raising any new alarm about the present-day hazard facing coastal communities, a distinction worth holding on carefully whenever a headline built around words like breaking apart starts to feel more dramatic than the underlying science actually supports. There is a useful piece of history worth understanding here as well, because this specific stretch of ocean floor near the Juan de Fuca and Explorer Plate boundary has drawn scientific attention for genuine seismic activity well before this particular tearing study was ever conducted. Years earlier, a swarm of nearly 3,800 small earthquakes detected in the same University of Washington, Oregon State University, and NOAA scrambling aboard a research vessel specifically to observe what was happening, with scientists at the time describing the swarm as consistent with active seafloor spreading, the process by which new ocean crust forms as plates pull apart from each other. One oceanographer involved in that earlier expedition noted the swarm represented a tremendous amount of energy released over just a few days, even though the activity was occurring far enough offshore that none of it was felt by anyone on land. That kind of documented ongoing seismic restlessness in this exact corner of the Pacific fits naturally with what this newer imaging study has now confirmed directly, that this particular junction of plates has genuinely been an unusually dynamic, actively evolving piece of geology for a considerable stretch of time, rather than a quiet boundary that suddenly and unexpectedly began tearing apart only recently. It is also worth being clear about the timescale this entire process actually unfolds across, since that detail matters enormously for correctly interpreting what getting worse genuinely means in a geological context. The kind of slab tearing and gradual subduction shutdown this study documents plays out over spans of thousands to millions of years, not the kind of time frame that translates into any specific imminent change in day-to-day earthquake risk for anyone currently living along the coast. Researchers studying this system are not describing a process accelerating toward some near-term climax in the way that phrase might imply in an ordinary news context. They are describing the continued, ongoing progression of a geological transition that has already been unfolding for a very long time, and will likely continue unfolding for a very long time. Yet, with each additional study simply sharpening scientists' picture of exactly how and where, that transition is currently playing out beneath the seafloor, one imaging survey and one research vessel expedition at a time. None of this diminishes the genuine, separate earthquake hazard the broader Cascadia Subduction Zone poses to the Pacific Northwest, a risk that exists entirely independent of this specific tearing discovery and that seismologists have been studying and warning about for decades on its own merits. The region's last major rupture, struck in January of 1700, an earthquake large enough that its resulting tsunami crossed the entire Pacific Ocean and left a physical record in written accounts as far away as Japan, discovered decades later when geologists cross-referenced Japanese historical records with buried tsunami deposits found along the Pacific Northwest coastline. That cross-referencing matching a specific unexplained tsunami recorded in Japanese coastal villages against layers of sand and marine sediment buried in Pacific Northwest estuaries allowed researchers to pin down the date of that earthquake with genuinely remarkable precision for an event that occurred more than 3 centuries ago, long before any seismograph existed anywhere on the planet. Millions of people currently live within the hazard zone of that same broader subduction system across Washington, Oregon, and Northern California. And the eventual return of a comparably large earthquake along that megathrust boundary remains one of the most significant natural hazards facing the United States, a risk this particular study neither increases nor diminishes, since it concerns a structurally distinct segment of the boundary further north. Seismologists generally estimate the odds of another major Cascadia rupture within the coming several decades at meaningful non-trivial levels, though pinning down an exact probability remains genuinely difficult given how few well-documented ruptures of this specific system exist in the historical and geological record to draw from. So what does all of this actually mean if you live anywhere across the Pacific Northwest? OR are simply trying to understand this discovery accurately. The practical earthquake and tsunami preparedness guidance for anyone living along this coastline has not changed as a result of this specific study and continues to reflect the same underlying Cascadia megathrust risk seismologists have been documenting for years. Know your evacuation route. If you live in a coastal tsunami inundation zone, keep an emergency kit stocked with water, food, and medication. Secure heavy furniture and shelving that could fall during strong shaking. And understand that strong or prolonged shaking near the coast is itself the natural warning sign to move to higher ground immediately, without waiting for an official alert that a major offshore earthquake may not leave time to issue. If you live specifically near Vancouver Island, or the northern end of this system, the same general preparedness principles apply, even though the tearing process documented in this study unfolds far too slowly to translate into any specific, actionable near-term warning of its own. If you are simply following this story out of scientific curiosity rather than direct personal risk, the genuine takeaway is that this represents a rare, direct observational confirmation of a process geologists had only ever reconstructed indirectly before, a discovery with real value for understanding subduction zones and the earthquake and volcanic hazards they produce in similar settings anywhere else on the planet, not simply within this one specific corner of the Pacific. Researchers studying subduction zones from Japan to Indonesia to Chile all stand to benefit from a clearer, observationally grounded picture of exactly how these systems behave as they approach the end of their geological lifespan, since the fundamental physics involved apply well beyond this one specific stretch of the Pacific Northwest coastline. The honest, grounded summary is this. Researchers led by Louisiana State University's Brandon Shuck, working alongside scientists from Columbia University's Lamont Doherty Earth Observatory and several other institutions, have published the first direct observational evidence of a subduction zone actively breaking apart, documented in the journal Science Advances. Using seismic imaging off the coast of northern Vancouver Island, the team found the Juan de Fuca and Explorer plates tearing into distinct microplate fragments along the Nootka fault zone, with one measured fault showing a slab drop of roughly 5 kilometers, a process the researchers describe as unfolding gradually, piece by piece, rather than through any single sudden collapse, with the overall subduction margin in this specific corner of the Pacific expected to shorten by roughly 47 miles over the long term as the process continues. The study's own authors have been explicit that this discovery does not change the known hazard posed by the broader Cascadia megathrust further south, the system responsible for the region's largest earthquake risk, and the same fault that produced the catastrophic 1700 earthquake and tsunami still remembered through both native oral history and Japanese written records, since the tearing documented here is occurring specifically at the more structurally complex northern edge of the boundary. What the discovery does provide is a genuinely unprecedented real-time confirmation of exactly how subduction zones eventually shut down, information that will sharpen earthquake hazard models in comparable settings worldwide, even as the underlying process itself continues unfolding across a timescale of thousands to millions of years rather than anything approaching an imminent human timeframe. We are going to keep tracking research on this system as it develops, sourced the same way we did today, straight from science. Advances, Louisiana State University, and the research teams actually studying this exact stretch of the Pacific Northwest coastline, not recycled headlines dressed up as breaking news. Subscribe so you do not miss it if follow-up research refines this picture further, because based on how much attention this particular corner of the Cascadia system has already drawn from researchers over the years, it likely will not take long for the next update to arrive. And leave that comment below. Tell me if you live near the Cascadia Subduction Zone and whether learning about this specific discovery changes how you think about the broader earthquake risk your region already lives with day to day. Because separating a genuinely fascinating scientific finding from an unrelated pre-existing hazard is exactly the distinction this entire video has been trying to draw clearly from start to finish. Because behind every one of these seismic images is a graduate student on a research vessel off Vancouver Island, processing months of sonar data, one fault segment at a time, a geologist finally seeing direct evidence for a process their field had only theorized about for an entire career, a hazard modeler somewhere quietly updating a regional earthquake simulation with genuinely new, observationally grounded data for the first time in years, and a family somewhere along the Oregon coast going about an entirely ordinary day, living above a tectonic system that is quietly, slowly, and on a timescale far longer than any human lifetime, still in the process of coming apart. 5,000 likes on this one. Let us go. See you in the next one.